In this video, I answer my students' questions and then we move on to solving the applications of quadratics. Enjoy. Okay, let's give it a shot. So, one of the questions that came up that won't actually be in the recording because I hadn't figured out a way to share that additional screen, at least not in time, was this question here about finding the inverse of a series of exponentials. So finding the inverse using TI gave a relation. When using the class pad, it was as a neat function. So I'm not super sure exactly what kind of function would be given for the inverse of f of x. One thing I can say is without any restrictions on the domain, you're going to run into some issues with the fact this is not a one-to-one function. So what I've got here essentially is just the graph of that function that we're looking at here for finding the inverse of. You can't find the inverse of anything unless you have a one-to-one function. And so somewhere along the way, you would have to restrict this domain at x equals 0 if you wanted to maximize your domain for this. Now, as for how you go about doing the inverse, one of the typical ways of doing that is to swap the x and y and then solve for y again, essentially. But this time doing it in the CAS itself. Now, that didn't seem to work. I hoped that if we put a domain on it, so saying that x was greater than or equal to 0, I hope that might try to change things on the TI Inspire. Didn't seem to work out too well there. So I wanted to maybe just double check, making sure I was actually finding that turning point correctly and trying to get my graph from there. Still wasn't quite super great as far as a solution goes. So I compared that to what the Casio would give. Sorry, just a second, we got a question here. Hi, Chris. Lost a mark because ClassPad got that. You use TI. Yeah, so I'm looking through this now, basically. So I'm not 100% sure why you got this, well, why the TI Inspire doesn't give this. I know the reason why there are two possible solutions here is because this actually is a relation, right? It's just that you have two possibilities here. Did your question come with a domain associated with it? I don't know if you saw the beginning of the lesson, but this is not a one-to-one function, so it won't have an inverse unless you've made it one-to-one. Point being, it would then let you choose basically which of those is the actual, yeah, okay, 0 to infinity, sure. So that would mean basically doing the inverse of, if I were to grab this and then just say x greater than or equal to 0, then you'd try to put that in there. And so you're only finding the inverse of this particular thing. Yeah, after the inverse it was minus 1 to infinity. Yeah, because that's the range. Makes sense. Range of the original should give you domain of the inverse. Yeah. As for actually getting the CAS to spit that out, it's another story. So for whatever reason, just doing the usual, which was swapping the x and y and resolving for y, didn't quite work. I was hoping that putting a domain on x might be helpful. Maybe now that I've put a domain on the function, maybe that'll work. Nah, still not quite. Okay, what else could we possibly do? I wonder if there is a actual function in here for inverse. Use lazy math. Gave you whatever you do. Yeah, okay, so it gave you the same thing. I'd have to probably spend a bit more time looking at this, see if I can get the TI Inspire to spit out the correct thing. I'll write that out as something that I should have a look at, and I'll get back to you on that at least after the class, and maybe put it in the recording as well. for like at the end of the recording. Okay, so go through inverse. So a bit weird, TI Inspire isn't quite giving the same results. For those who do have Casio, you would basically look at these and compare which one of these would actually give the proper inverse. Reminder that inverse is a reflection in the line y equals x. So if your graph already looks like this, then you want to pick the one that essentially makes it go like this, as far as a curve is concerned. And that would mean probably taking the positive logarithm. Okay, you got a logarithm there. Okay, well, they're both positive logarithms. So basically, you would graph both of these and see which one would be which. So if I go, oh, that's not going to really work out well. Okay, I'll just zoom in on this one and copy it over. So the first possibility was natural log of negative square root x plus 1, and then there was a plus 1 inside that again. Yeah, it was inside it. And already we can see that's not quite right. It's pointing down. It's not even close to flipping in a line y equals x. So if we flip that around to pick the other root, which would have been get rid of the negative on this, and that's it, we see we now get a proper inverse. To really hit that home, if you have it along the line y equals x, you'll see it's a perfect reflection either side. So that's the gist of it. I know that's what you were trying to do, but obviously the TI Inspire didn't quite get that there. As for the other things we've got in here, so we've got functions f and g, two separate graphs there. Which of the following best represents the graph with the g of negative f of x? Okay, it's a fun one. So just for the sake of the recording, I'll copy down what that's looking like. So what we have is, section that off. We have g of x, which basically looks like a cubic. That's our g of x. And then we have f of x, which is a kind of, what do you call them, piecewise. That's right. You have f of x, which is essentially that. And so what we're trying to do is do the graph of g of negative f of x. Inverse modulus looks like reflection in the x. Yep, reflection in the x, absolutely. So the starting point, yeah, just like you have on your picture, would be to flip that in the line y equals it, in the x-axis rather. So you'd flip like that, and then essentially it would be as if you were subbing this graph into this spot on G. So the y values of this are the x values of this. So if we look on the positive side of things, so we get our other axes, starting at the dead center, this is going to give you y equals 0 no matter what. That's going to mean x equals 0 on the G, and then that's also going to mean y equals 0 as a net result so far. So for everyone else, basically all we're doing is taking key spots along this reflected graph and then subbing them in as x values on this, and then dotting out the graph accordingly. If anyone needs me to explain that in any more detail, let me know. Otherwise, I'll just keep subbing in some values. So we have x equals whatever here. That's y equals something more positive. Question, wouldn't the inflection point remain? Yeah, you've got x equals 0 there. It may not be an inflection point anymore. I guess we'll see. But yeah, that point 0, 0 is still going to be there. Yeah, okay. So for those who, for the recording, this was a multi-choice. So yes, you can ignore some of the questions there, disregarding A and C. Well, it's not necessarily an inflection point. I wouldn't be so certain to say it's an inflection point, just that 0, 0 would be there. I would continue to dot this out. I mean, maybe it is. But okay. So that becomes there. And what you're essentially seeing is this kind of graph. Confused why you achieve symmetry in B, not in D. Well, B and D are completely separate answers. They're not like it's not like they both came from a graph. They just kind of made up their own whatevers. Initially circled D. Yeah, I mean, multi-choices are just sort of whatevers. It would mean that in the cubic. Okay, well, while you type that out, I'll just continue to draw the graph. That, or we can come off on mute and we can have a conversation about it. But okay, so on this right-hand side rather, these y values become the x values. You're basically going to get the shape of the cubic from that. And then on this side, because these are positive y values, those become positive x values on this. And so all you're doing is getting a reflection there. And it should be, because these are the same slope, this should be the same. There should be a mirror there. And that's why you get B. Now there's a bit of bowing in there on the actual multi, but that's the gist of it really. Mirror because you always choose the right hand side, but specifically because the y values of this are the x values of this. So that's that one. Next one is same deal, kind of speaking. So we got f and g on the same axes. G of f, yeah, so same kind of question. So from there, all we're doing is, well, first things first for the recording, I'll copy that down. Okay, so we have f, which is quadratic. There's f, and then g, which is a hyperbola. ... And okay, it looks like just some generic hyperbola, nothing crazy. That's going to be our g. And so again, same idea. We're doing g of f, and we want to figure out what that graph might look like. So g of f simply means whatever the values of f are, those y values become the x values of g. Now, this one's a bit on the crazier side, I'll say that much. So best to portion things off in sections. So you can imagine doing like right-hand side, dead center, and left-hand side. What's going on there? The way it works is you work from inner to outer. So we're trying to do g of f, which means we start by figuring out, we start by partitioning it some x values, so we can get something to dot out over here. And we check the y values at those spots. Those become the kinds of x values we test on G. So easiest one potentially to start would be at x equals 0, you get y equals something quite positive, which means x is something quite positive over here. So the y value is going to be something like this. Wouldn't the graph have to be less than 0? Well, so far it is. That will be this initial value here. For all x is an element of R. Well, we're looking at part by part, right? We're getting there. And so you could imagine as x is getting, yeah, f of x is always greater than 0. And thus G receives all positive inputs. Yeah. So you can see f being the fact that it's always positive. Now the thing is, you want to get shape still. So you can say the graph is always below, but you also still care about shape. So sure, it's a nice observation, but you still want the shape, really. So anyway, all you would do is continue dotting out at these key spots. So this one will be a smaller y value, and so you could imagine a much more negative thing going on here. So I could imagine, you can see as the y values get smaller, that means x values get smaller on this, and so as you go right, you go down, essentially, on that. But only to a certain point. once you hit this turning point, you start going back up. And so you should effectively have this curve that does that on the right-hand side. Because this just means x values are going like this and then like that. Oh, sorry, other way around, like this and then like that, which is why you're getting this portion of the curve. Then on this side, it is, so as x gets more and more negative, y values get more and more positive, which means we're getting this portion of the graph. Please explain how we got that shape again. Yeah, this is a very tough one. I'll put it that way. Very complicated what's going on. But for now, this is the net shape. What I'll do is, yeah, that is the net shape. So take a quick photo of that, or I'll come back to it later. And what I'll do is I'll draw these on their own separate axes, and that way we can see a little bit better as to what's actually going on there. Because when it's overlaid like that, it's kind of on the tougher side. So what we have is quadratic, which is like this. This is f. We also have g, which is hyperbola. I think I labeled those right. Let me double check. Yeah, f is quadratic, g is hyperbola. And the thing that we care about is g of f of x. Right, so this is back to basically composite functions, which means you start with some x value, that gets fed into f, then the y value that comes out of f goes into g, and then out comes a y value at the end, like the final y value of this function. So we're basically going to keep track of that for key x values along the curve, and then dot out the final result. The way I like to do it is start at 0, look for turning points, any key feature kinds of stuff of the graph is what you'd want to try and observe. The easiest one to look at by far would be to start at x equals 0. So if you imagine x equals 0 is this, that gets fed into f, and imagine this was like, I don't know, let's call it 3, just for whatever reason. That means that a 3 is coming out into g as an x value. Let's say 3 is approximately here. That's going to give us, so what comes out of g is, I don't know, -1, let's say. We're just sort of eyeballing it as far as proportionally. But that final -1 is that y value. So when x equals 0, I give y equals -1. So this is the spot on the graph of g of f of x. We do that for key points on this graph and then get the shape from it. Is at least the process clear enough on what's actually happening there? Because this is, definitely on the tougher side. Got it. Nice. Cool. Okay. So, I'll do a few more key points. The kinds of things I would be looking for would be turning points, because that's when you get changes in what we're looking at. Changes in, like, from y, positive y to negative y, changes in positive x to negative x. These are all the kinds of things you would be looking at. Could be really easy since it's multi-choice. Well, if it's multi-choice, it's CAS. And so at that point, you just choose, like, you could, as long as you know enough about functions, you could just sketch this on the CAS. If it's tech active, for sure. So, like, you just need any positive quadratic on the right-hand side. So if I literally just did, like, I don't know, let's call it x take 2 squared plus, well, if I can click the buttons correctly, that'd be good. Yeah, x take 2 squared plus 3, sure, that'll do. That'll give you one function, and then just a simple 1 over x would suffice for a, well, I guess the other way around actually, -1 over x. And because it's g of f, you do, so f5 of f4 is what it would look like in the CAS. So f5 of f4. And then, you get that orange line, which is kind of hard to see. So let's change up the window a little bit. Let's do it from like -1 to 10, and then shrink this all the way down. Geez, even that. Beta 1. And so that yellow line is the net result you're looking for. Yeah, it wasn't a camera thing, it was more a window setting. Camera can't really come much closer than that. And so yeah, basically it would just be subbing the functions into each other. That's if you're doing tech active. Tech free, it would be like I described, which is dot everything out and then you're sorted. Okay, those are those. Shall I dive into that in any more? Oh, hang on. Get equation of f of x in turning point. Oh wait, sorry, I'm looking at the older questions. What am I saying? Yeah. Should I dive into any more detail on that, or are we good to move on to curriculum content? It will be quadratics, by the way. Applications of quadratics. Easy. Okay. Let's change the screen share over and let's get into it. The class is an hour in total. Yeah, you're good, Krish. No worries. Let me just find the right. There it is. Cool. Yep, good to go. Okay, so quadratic models. We were doing 3L. Okay. We got the notes for that. Quadratics, applications of quadratics. Okay, double checking this is all good. I am in fact screen sharing the right things. Yes, cool. Okay, so first thing we'll look at as far as curriculum goes is the families of functions, style questions. So the whole goal here is that you have some generic quadratic, some generic any function, really. In this case, we'll just look at quadratics, that has some A, B, and C's, or whatever number of unknowns that are part of the graph. And your goal is simply to take the information that's given to you to solve for those unknowns in the graph. So this could be your full quadratic form, it could be factorized form, it could be turning point form. Those are the three main things, at least in the context of quadratics. So the format that you use will simply be dependent on the information that you actually have in the question. So for example, if I had a turning point and a point, then all we're really doing here is using the turning point form. The reason why is because turning point form tells you the location of turning point. So if you know that your turning point is at 1, 3, well, that means you're going to have x minus 1, and you're going to have a plus 3 at the end. The key advantage there is that you have 1 point, but you've solved 2 unknowns with that 1 point. Yeah. So from there, you're always going to have this a value that's left over. In pretty much every case that I've ever seen, you solve that a value by rearranging for rearranging for a rather, after you sub in another point. So in this case, you have x equals 0, y equals 4. You sub those in, you get your a equals 1. So depending on what the question's asking, it may say give the final rule, in which case you give this answer, or it may say give a, b, and c, in which case you'd give a equals 1, b equals -1, and c equals +3. That's about it, really. If you instead had, just got a question real quick. Questions where you get the info at turning point, do dx equals 0 at x equals 1. Yeah, it's another way of doing it. So that's for calculus, if anyone's actually up to calculus yet. Saying dy on dx equals 0 just means gradient equals 0, and all turning points or any stationary point will have a gradient of 0. So that's another way that you might be told the turning point, and that's your prompt to use turning point form. It's just another way of phrasing a turning point. So you would still use this this form of the quadratic to solve that. If you instead had axes intercepts, specifically the x-axis intercepts as your key features, then the best form for that would simply be to use the x-axis intercept form. The reason why is because null factor law will always tell you where your x-axis intercepts are. So if you know they're at -2 and +1, Well, there's your factors, x plus 2 and x minus 1. As I said before, all you need to do to solve for a is sub in an additional known point, in this case 2, 12. So all the x's are becoming 2's, and the y is becoming 12. Rearrange for a, give the final curve. Worst case scenario, you've got 3 random points. So under those circumstances, this really worst case scenario could become a 3-way simultaneous. If you're lucky, or rather, if the assessor was nice, they would give you they would give you like the y-intercept. The reason why that's kind of lucky is because when you have x equals 0, your plus c value will always be whatever the y-intercept is, simply because everything else disappears. So in this case, it's just a 2-way simultaneous. So you sub in -1, 10, that's this, simplify it all the way down. You sub in 1, 4, that's this, simplify all the way down, and then use whatever simultaneous methods you like to use. I've got elimination method here. You could do substitution or whatever else you like to do. In any case, you're going to get your solutions for A and B. We already had one for C, and then then that's your curve. One more question from Krish. Looking at a practice sack about a robot. Passes through 3 points, 2 points they give you. Last one is your choice. Yeah, sure, that's fine. If you had an equation that was already in there, hang on. Can you find an equation of those 2 points they give you, and then give the third one? I would have to see the question, man. If the point was on a function, the full function was unknown, is what you're saying? Yeah, I mean, look, depending on what information you had, would be one of these 3 examples. If it was quadratics, anyway. Send me the question afterwards. I'll have a look at it. But okay, so maximum/minimum problems. So the idea here is the vast majority of the time, whenever you're trying to find the maximum or minimum of a certain quantity, it's pretty much always going to be a turning point. Now, not necessarily guaranteed. We'll look at a few different cases, but the vast majority of the time, we're finding turning points. So this kind of framework can help you solve those application style questions, the ones where you've been given a certain scenario that you're working with. And simply put, we start by trying to find the equation that describes what we care about. Usually it's some form of area. From there, you're just going to sketch your function. That way you can clearly see what's going on in the function, where the biggest y value or the smallest y value is. That's what step 3 is all about. And then step 4 is just find that y value using whatever methods you can. If it's a turning point, use turning point methods. If it's an endpoint, you're just going to sub in that x value. So we have an example here, which is rectangular garden, 20 meters total of fencing wire. So a full perimeter would be 20 meters. What is the maximum area that can be enclosed by the wire? Now, the way these always work, whenever you have a rectangle, just a quick pro tip for this one, maximum area is always going to occur when the rectangle is a square. That's just always the case. And so if you think about how you distribute your 20 meters of fencing wire, just make it into a square, so 5 by 5. That way you've got 5 across all the side lengths, and then 5 5s are 25. So that's a quick little hack for any of these ones when it's just talking about rectangles and maximizing area. However, not all questions are that simple. That's why we have this kind of framework to help us out with pretty much any situation rather than that specific one. So, first up, what is the equation that describes area of a rectangle? Well, just length by width. Now, the problem here is that you have 2 variables in there. You have a length and you have a width. If you want to sketch this, you need to have only one variable. It doesn't matter which one you have, whether it's length, whether it's width, you just need to have only one in there. The way that works, you've got some additional information in there that can allow you to create a second equation, which you can then rearrange. So the fact that our total perimeter is going to be 20 meters means that, well, perimeter equals 20. And if you think about how the rectangle works, you're going to have two lengths, you're going to have two widths that make up the total perimeter. So that gives you your final equation, 20 equals 2L plus 2W. Doesn't matter which one you want to rearrange for. In this case, I've chosen to rearrange for W. So once you have your W, you just replace that W from the area equation with your 10 minus L, thus getting your full quadratic equation out of this. So because there's only one letter left, we can put A on the y-axis and we can put L on the x-axis. There's no more weirdness going on in there. So let's sketch it. If you sketch over the full domain of a normal quadratic, it would look like this. It's cutting at L equals 0 and L equals 10, as per the null factor law here. But that's not quite the valid maximal domain for this, because you need to remember, this on the y-axis is area, and on the x-axis is length. So when you're thinking about application style questions, you have to consider, can these quantities be positive? Can they be negative? Can they be zero? All sorts of questions like that start to arise. The gist of it is that things can only ever be positive. All right, positive area, positive length, and so pretty much everything below here, that's going to be cut off. Yeah, area greater than or equal to 0. Correct. So that's the gist of it. You cut off at those spots. Sometimes this quadratic will be shifted over to this left-hand side instead. Or apps questions, can you find the maximum min without sketching? Yeah, so you can find it without sketching. You just have to be pretty good at picturing the graph in your head. Because, yeah, you have to be good at picturing the graph. So if you already see in your head that the maximum is going to be here, then by all means, go straight for that. Now, in the next thing, we'll look at what happens when it's not a maximum. So you've also got to run the risk of making sure that you can picture this as well, which we'll look at in the next example. But yes, to answer Chris, you could do negative b over 2a after expanding this if you wanted to find this. A lot easier would be to just find the midpoint between 0 and 10, because turning point will always be midpoint of the two x intercepts. But yes, that does work. Either's fine. Point being, once you have your graph, look at the y value. We can see it's a maximum. So we may not know exactly what the y value is, but we can, as I've just stated, know what the x value is, either by midpoint or expand out negative b over 2a. You could complete the square. Any quadratic method will get you there. Okay, once you have that x value, or in this case it's an L value, you just plug that back into your area, and that's going to give you the 25 meters squared that we knew from the very beginning. But as I said, this is more important for the more complicated things. Is this methods 1 and 2? It's a bit of a mix. This used to be a Q&A class, actually. So I've kind of just thrown together some classes to offset the others. So we're doing different things at different times. But yeah, the book that I'm using is from Unit 1 and 2. It's the same as 3 and 4. Nothing's actually different, really. At least not for quadratics. Okay, so from what I was describing earlier, sometimes it's not quite cut and dry. Like, sure, you might be able to picture the graph, but restrictions on the graph, a bit harder. So in this case, one length cannot exceed 4 meters. So it's like, okay, sure, I might know my quadratic in my head looks like this, but when you think about like length, now you got to consider, well, hang on, what did I put on my x-axis? Can be a bit more complicated. Basically, follow the same steps as before, so nothing's changed up until finding our equation and drawing our graph, but now we only care about our domain from 0 to 4. Now we want to put that length on our x-axis. And so from there, if you're now only looking at this section of the graph, now this is your maximum, not this. And so all you're doing is having an L equals 4 at that spot. So that's the only thing I'd be worried about by going straight for the end. If it's not there, if it's clear, cut and dry, then by all means, use any shortcut to get you there. That's no worries at all. Any questions on any of those two concepts? Okay, done these. I think the chapter review has some nice stuff in it. That's a good spot. Yeah, let's do question 3. This one's got a visual actually. Let's work with this. Okay. So these being extended responses mean they are tech active. We're now just going to go through some of these. Okay, so question 4. Point P is x meters from B along the line BC. So there's our P there. Find the distance PA in terms of x. So PA meaning this sort of diagonal up here on the screen share. What might we do? While you guys have a think about that, yeah, Pythagoras is correct. That'll be the approach, but we've now got to think about how we can utilize it exactly. So I'll start drawing it out on the handwritten bit. There's one key piece of information that isn't currently on the diagram, but is in the written bit. So we care about this. To use Pythagoras, we need 3 things. Or at least, well, I guess 2 things, technically. We're missing one of them. It does say find distance in terms of x. That's a bit weird. There's no x on the diagram yet, anyway. Where should it go? I'm not sure what. Oh, hang on. It says B is x meters from P, hence the bottom is x. Precisely. So there's this statement up here. The point P is x meters away from B. And so if you take B as your origin, essentially, it means that this distance here is x. So when you think about all the sides of your triangle now, if this is your A, this is your B, and this is your C, because C is hypotenuse, then now we've got our Pythag all sorted. So you got x squared plus 5 squared is equal to, I guess you can call it PA squared, why not? And then obviously, once you have this, if you want to find PA, well, you're just going to square root both sides of this. And you're going to make sure it's only positive because distances can only be positive. Square root of x squared plus 25. Fair enough on that one? If not, let me know. Otherwise, we'll move on to the next one, which is finding the distance PC in terms of x, which would be this horizontal. Yep, 16 minus x is correct. That's it. So if this total distance here was 16, and this bit in here is x, then if I subtract this x away from 16, this is what I have left. PC equals 16 minus x. Okay, Sanjay, so for distance of PA, you can't simplify further. Not quite, nah. So this would end up being a semicircle. Yeah, yeah, so it'd end up being some kind of... Oh, no, not actually a semicircle, sorry, there's no subtraction there. Well, normally, yeah, I'm not 100% sure on that, because as x gets larger, I think it's just a big root. Yeah, I don't think it's anything semicircle. Semicircle needs a subtraction. Square root x squared plus 25. Alright, sum's gone up. What if I manufacture A? Yeah, checks out. Didn't think it would do anything super crazy. And the reason why it's defined on the left-hand side is because all the x values are getting squared. So that's why it's still allowed. Yeah, nothing else to really be simplified here. You might make this back into 5 squared, so it looks kind of like the generic form of a semicircle, but it's not really a semicircle. Should write x is greater than or equal to 0. Yeah, no, fair enough. Should write x is greater than or equal to 0. Sure, yeah, that works. X greater than or equal to 0. Can't go wrong with that, really. It's kind of implied because if x is a distance, then x has to be positive. So I wouldn't say it's strictly necessary. When you take square root x, you could justify why you reject the negative branch. Yeah, you can write a sentence there to justify it, if you're worried about that sort of thing, yeah. Because, yeah, normally you'd put plus minus for any roots, but as I said when I was doing it, when it's teachers are moron. Sure. Yeah, so you can put that in there and then have a little statement saying dist equals positive, therefore only positive square root. And yeah, you can put all this extra stuff around it if you're worried about losing a mark. A reasonable assessor shouldn't care about this. Okay, so that's PC done. PD in terms of x. So we're now talking about this here. So P to D should look kind of similar. What are we thinking? So we're doing B double I, which is find this distance P to D. Yeah, Pythag again for this one, absolutely. And this time we already have it using the 16 minus x because this is 16 minus x here. So 16 minus x all squared plus the 3 squared from that is equal to PD squared. And so again, you could put all this other fancy stuff if your teacher is a quote moron, or you could trust in the basic common sense. plus 9. And so again, you couldn't really do a whole lot with simplifying this beyond that. Because yeah, and a decent way to check that if you're doing this alone, by the way, is check if your CAS actually simplifies it any further. So if I go into my CAS and I print F7 again, because that's what the function was, does it actually do anything with it? And in this case, you can see it doesn't. So the CAS will always try to do some fancy whatever to make it look simpler. If it doesn't do it, then you can be pretty safe to know that there is no simplification. Obviously, you can't do that in the exam, but doing that in the questions that you come across here would be well, as in you can't do it tech-free, obviously, but doing it here, that way you can at least know ahead of time. If x equals, find x if PA is PD. Okay, probably shouldn't have moved the camera there. So find x if PA is PD. That's the question 4C there. So we had PA, which was this one, PD, which is this one. Find x if they're the same. What might we do to start this off? Let them equal to each other and solve. Precisely. This is a CAS question, I just remembered. This is tech active, so you could mess around with that. In tech free, not so much. Even solving this tech free wouldn't be the end of the world, because you would just start by squaring both sides and then solving the quadratic afterwards. But it is tech active, so let's cheat for the just so we can get through things a little bit faster. So menu 3.1, we had PA, which was the square root of x squared plus 25, and then we had the other one, which was the square root of 16 minus x squared all squared. Oh, sorry, no, not x squared. 16 minus x all squared plus 9, comma x. The syntax will be the same either cas that you do. That's going to give you x equals 15 on 2, which is what was required. Find x. Q5 looks good. Sure. Let me just, oh yeah, because D and C are the same thing. So find x if PA was 2PD. Let's just briefly talk about what you would do for D and E before moving on to it. What would you do in D? Introduce 2 in front of the right-hand side and solve, yeah. So reminder that this right-hand side was PD. So that was this thing. So 2 times PD would mean 2 times this. And so if you put a 2 at the front here, you're going to get something nasty. It does say to it the 3 decimal places. So you'd control enter on this cas, or you would click the decimal button on the other cas. Now you've got 2 possibilities there actually. You've got x equals, yeah, you got x equals 10.8-ish, and you got x equals 31.8-ish. Now, here's what our thing looks like. We've got 2 possibilities, x equals 10.8, x equals 31.8. I know that's not rounded properly, it's fine. Now here's the thing, do you give both answers? And if not, why not? $10.8 is more reasonable, yeah. 10.8 is correct, but what's wrong with 31.8 specifically? What makes it unreasonable? Too large? Yeah. These are all correct. Curious to hear, like, what makes it too large? Domain on X? Yeah, domain on X specifically. What is the domain of X? How big could it possibly be? Yeah, there you go. X is a part of 16. So if you were to give possible domain of X, what are we thinking? So if you were to give a domain on X, what would it be based on what we just discussed? Is my mic still broken? Let me double check. Test. Okay, maybe his audio broke. Basically, because X is a part of this, yeah, so you could do 16 minus X is greater than or equal to 0. 16 minus X, yeah, kind of, because that will make X the possibility of negative. Okay, we got 0 less than or equal to X, or less than, yeah, so basically between 0 and 16. So to give you some syntax around that, you would say X is an element of, now does it allow zeros? That's always a bit ambiguous. If it doesn't say, then it can include it. You'd basically say 0 to 16. Yeah, that's the syntax you'd use for that. You could use, what else could you use? Inequality notation. So the better way of doing that would be to say 0 less than or equal to X less than or equal to 16. That's if you want to use inequalities. That's the slightly better notation there. Because since the side exists greater than or equal to 0. Yeah, so basically, yeah, it can't go negative is why we've got to put a lower bound on 0. That's why we're doing it that way rather than just saying everything less than 16 minus X. Cool. Okay, that's the gist of that. Part E was just a repeat of exactly what we just had, which is now 3PD. So again, we're going to have these same issues. One of them's going to be too big, one of them's going to be too small. Yeah, it could be greater than 0. The question doesn't necessarily say that x couldn't be 0. That would put p right here. It's, the actual exam will have more bulletproof wording around it. Every time it's come up, it'll say, hey, area has to be positive, which means can't be 0. In this case, there's nothing I'm looking at there that justifies that x can't be 0. But that's, I guess, up to interpretation, really. Wouldn't be greater than 16. Yeah, okay. So it is between 0 and 16. It's either going to be square brackets or rounded brackets, depending on who thought what about it. The question should be more bulletproof in that regard. Because if you think about the extremes, if x equals 0, p is here. If x equals 16, p is here. Anything else would put p outside of the thing. That's the gist of it there. Okay, that's that. Moving on next. Question 5. A, B, C, D are crossroads. Jogger runs along A, B at a speed, passes at 1 p.m. Okay, whole bunch of information. Y kilometre, be their distance apart t hours after 1 p.m. Find an expression for y in terms of t. So basically, how far apart are they in terms of t? Brilliant. Okay, so start having a think about that. I'll draw it down just so we can start referencing it on the handwritten bit. Biggest thing you have to realize is diagram is not quite the Cartesian plane, although no, it has an origin. It just means that y is not d. That's the main trap there, I would say. And t is not b. It's a little bit weird. Passes O at 1 p.m. Oh, okay, so actually starting from the left and bottom. So putting 8 kilometers per hour there is actually kind of nasty, because it tells you in the question that both of them pass the origin at a particular time. And if they're running in this direction, well, that means it really should be over here. Unless I've misinterpreted that. Let me quickly double check. Jogger runs along AB, so that can be like J1, jogger 1. Passes the origin at 1 p.m. Any way it can pass the origin in that direction is if it starts on the left. And second runner passes origin at 1:30, so this one's in the right spot, J2. Alright, so we got some speeds, we got some times, and we care about distance. How's that all run? How's that all work together? Even if we ignore the question, if you've got stuff with, you can put t on the x-axis and y on the y-axis. Oh, speed on the y-axis. Yeah. Technically, wouldn't CD and AB be the same? CD, AB. It's talking about the cardinal directions of each other. So the fact that they're running perpendicular to each other will end up mattering, because y is the distance between the people, not the distance between where they started and where they ended. So basically, if I had a guy over here and a guy over here, then that's the distance. Whereas if they were running in the same direction, it would be like guy here, that's the distance. So one's using Pythag, one's using just a basic subtraction. That's why these are, although shouldn't necessarily matter if they were with respect to each other, because it's the combination of the two of them, now it matters the direction. But ignoring the specifics of this question, when we have speeds, when we have distances, when we have times, what kinds of equations come to mind to wrap these all up together? Linear? Yeah, it is a linear, technically. What equations specifically comes to mind? Anyone remember distance or speed equations? Yeah, I mean, look, it could look like y equals mx plus c eventually. Point I'm trying to get at is if you want to marry all these concepts together, then you got speed equals distance over time. If anyone does physics, I'm sorry, I'm using S for speed. Yeah, speed equals distance over time. And so if we think about like each individual jogger, so J1, you've got a speed, which was 8 kilometers per hour. You've got a distance, which is the unknown. We don't know what was traveled. And we've got the time it took, essentially. Now, because we're trying to create a, we're going to need two equations and subtract them, maybe. Might have to do a bit of Pythag. We'll see. But anyway, passes O at 1 p.m. We have given some points there, so we do actually have a time value that we could use. But because we're trying to create a distance equation, we kind of want to have a distance in terms of t. We kind of want to leave those as they are. So I'd say d equals 8t for jogger 1. And then jogger 2, well, that's 10 equals d over t. So J2 will have d equals 10t as far as, so this is distance in the horizontal, this is distance in the vertical. Now, tough to introduce Pythag now, yep. So I'm just trying to think about how we could put Pythag into this. That is a tough one. It's got to do something with the times. So passes the origin at 1 p.m. matters. Straight distances. No, well, yeah, no, you apply Pythag. Just trying to think of how you do it. Because, okay, well, let's say the net distance is going to be some, whatever this is squared plus whatever this is squared, all square rooted. So maybe it doesn't matter where they're physically located. Maybe I can just say y is 8t all squared plus 10t all squared, square rooted. Because 8t squared describes any path, or 8t describes any path along here. And, sorry, 8t was this one, sorry. 8t describes any path along here. 10t describes any path along here. And so any of these points, any of those points, Pythag is going to be like that plus that, sorry, this plus this squared, divided by, well, all square rooted. Does that work? Origin, distance in this direction. The weird thing, yeah, because the origin here doesn't actually, I don't know how I feel about that. I think I'd have to think about it a bit harder than just that, because this is a distance and they start at some unknown point over here. Because this is implying that they're, well, let's find out. If I sub in t equals 0, what do I get? Because that will tell us the quote starting distance of each other. 0, 0, 0. And that can't be right. So we haven't accounted for, yeah, exactly. Haven't accounted for the 1 p.m. and the 1:30 p.m., which I think the intention there is to be able to walk back what their initial starting points were. Geez, okay. You've got to get everything in terms of their initial starting point. That is a tough one. Okay, we have hit time. I'm just going to cheat for that one. So we had chapter 6. No, not chapter 6, chapter 3, review. I'll change the screen share in a moment. Let's see what they did. So if you guys want to see the answer, feel free to stick around. Otherwise, technically, class is over. Then a response. It was, what is this, question 5 of chapter 3 review. Okay, let me change the screen share. That do anything? Yeah, it did. Okay, so this is the part that we're looking at here. Okay. Consider AD, BC, Cartesian axes. First jogger starts at 8t commas, starts at 8t comma 0. Second jogger is at 10t minus 5. 10t minus 5 would be because 10t minus 5. 10t minus 5. Yeah, I know, right? A lot. Minus 5. What's going on there? Probably if you sub in those time values, you'll get something with 5 involved. Let's have a play around. Yeah, that's what I'm trying to think as well, Chandra. Okay, so if I do the first... Let's see. So the first equation was if you... So the first person passes the origin at 1 p.m. and t is the number of hours after 1 p.m. Okay. So first equation is going to have just t equals 0. So this guy actually started at the origin then. Okay. So first person starts at origin. That's good. And then this guy passed at 1:30. So that means subbing in point. Okay, that's where the 5 came from. So d equals 10 times 0.5, which is going to be your 5. And so this guy is starting 5 meters away from the origin. So, weird question. So because this is 5 meters initially away from the origin, what we're saying here is, where is it? 10t minus 5. 10t is saying how far in this direction is he going, in that direction. And so when you have 5 minus 10t, that's effectively saying you started at 5 and you're going in this direction, which means you're subtracting 10t, whatever that ends up being, away from that distance. Then you're doing Pythag on that. So I think, is that clear enough where that came from? Tough one, for sure. Bit lost. Okay. So it's like saying, if we just focus on that section, you've got, well, let me change the cameras around so I can actually look at the right thing. There we go. So you've got this distance of 5 away from the origin, and we're starting here. I'm running in this direction at, 10 kilometers an hour. So 10 kilometers an hour. If I run for 0 hours, I'm here. If I ran for 1 hour, I'm here. Oh, sorry, no, 1/10 of an hour, I'm here. And so the net distance for this axis is 5 minus 1. Or, in other words, 5, what we started with, minus our equation for any given t value. So this was t equals 1/10 of an hour. If we get to half of an hour, we're here. If we keep moving on, then we're getting further and further away. Is that a bit clearer why it's now 5 minus 10t? Yeah, this will be in your past recordings, Krish. So it'll be in the classroom tab in the past recordings. It'll take me like, I don't know, a day or two to have it uploaded. Still a bit lost? Yeah. This is definitely on the tougher side, for sure. I do unfortunately have another class to get to. Can't spend a whole lot of extra time on this. But basically what I'll leave you with is to think about the fact that if you test different values of time, as time moves on, distance keeps crawling up here. And so if you think about your net distance away from the origin, which is what this is, then whatever this is has to come from whenever we started. Yeah, I can send you a screenshot of the question as well, Krish. That's fine. It'll be all screen recorded. Yeah, but I'll send you specifically the screenshot. And so basically, the values that are coming from here mean you're crawling up this, which is reducing this initial distance of 5 until eventually it overcomes here. That will be the main thing that I'll be starting to think about. So, yeah, tough one. I'll try to revisit it at another time, or if you send me a DM, I'll put in a bit more detail. All right, that's about it. I'll let you enjoy the rest of your day.